observation.
Thank you very much, Rosemary. I have to thank Rosemary. I'm a co-organizer, but she did all the work, so I think we should give a hand to her. So I'm going to talk about work which started 4 years ago, and it was quite successful. So it's about optimal design for correlated observations. It's joint work with originally Andrei and Anatoly and I started, and recently Maria joined us, and we were already very successful in a paper which was written 2011, which is that's DPZ. This came out here, so we were thinking that was a quite good paper, but then we did even something better last year. So the same authors, this come out in 2015-16. It has been accepted this week. Now we think you can even do something more better. So I hope I can convince you about that, and we will see. Okay, so what you might don't know, so you need a little bit of about stochastic differential equations, not so much stuff, but you have to be more flexible than usually design people are. So, but it's not so difficult. So I try to explain everything, and that's the reason why I use the blackboard. So I should be careful here. So what we consider is the following model, which everybody knows. It's a linear model with some vector of independent regression functions and errors. But the difference here is that the error process is somehow correlated. So the process of correlated observation. So epsilon t is a Gaussian process. So Gaussian process is nothing terrible, just a family of random variables, and they have certain properties. They are normally distributed, and then you have certain covariances. Okay, and we have, so this is Gaussian process. So I put it here, and by the way, now it's the last chance. If you can not read it, you could go move a few rows forward. So I announce that anyway. So if you don't want to hear, it's also okay. So theta is what is the dimension? Theta is some kind of parameter, and f is a vector of regression functions. Everybody knows that. So if you cannot follow, or if something is unclear, then you just interrupt me. Yeah? Because it's a different way of thinking. So in this sense, you might not be used to that. Okay, so the important point now here, so that you have correlation between these things. So we have some kind of correlation, which is the expectation. So everything is centered here of the two noise points. So epsilon t is a centered Gaussian process, so I should put centered here. And Anatoly, in the second talk, will hopefully convince you that it's sufficient to consider only one Gaussian process. So we only have to consider one Gaussian process. That's what his job, what he's doing. So you can believe me, that's very clear that we only have to consider one Gaussian process. So what's your favorite one? The Brownian motion. So I take the Brownian motion here. So the covariance of the Brownian motion is S minimum t. Okay, so there will be Brownian motion. And now I'm a little lazy. Now I'm a little lazy, so yeah, that's okay. This is just a model that you don't forget it. Whoa, nobody is using this anymore. You see, it's so hard to. So I don't know. This is very
One of these things for pulling it
no, anyway, okay, it's very hard. Anyway, so I'm a little lazy now. So I mainly I write now. Assume this is for simplicity. Makes things a little simpler. I don't have to write so many formulas. So assume A is 0. I could have put that from the beginning. B is 1. Yeah, so that's not, it's for simplicity. You have to work a little harder, but then things getting more complicated. And I also assume that this thing here is a vector of the differentiable functions, and it should not be 0 somewhere. That's maybe not true, but so this should be not 0. Maybe at some point, but not at a full interval. Okay, and another thing what I want to assume to be correct, because Anatoly and Maria and Andrea in the room, so assume if this converges to 0. This is, you will not see it really, but this is just for the experts. So I have 3 experts and then they interrupt me, so it's not important for you. You don't see it. Okay? All right. So, and what people did before is somehow the classical way. We have the model, then we do least squares or weighted least square or what do you like, estimation problem, and then you do the optimal design. Okay, and if you know correlated, a little bit over the correlated observations, then they do some kind of asymptotics when n converges to infinity. So we're doing everything in a different way. So we don't separate estimation and design, and maybe a little bit at the end, but at the moment we do everything simultaneously. Okay, estimation and design simultaneously, so it's not a different way of thinking. And we go to the limit directly. Okay, that makes things a little more complicated. So our approach is maybe easy to describe. Yeah, estimation plus design. It's not quite true, but it's roughly, that's the way we're thinking, or at least I'm thinking that way. I don't know about my co-authors. Okay, so we do that simultaneously somehow, and then we go directly to the limit. We look at the limiting model. So what is the limiting model? So what is the limiting model of that thing? It's a so-called Gaussian white noise model, where you observe the full process. So the limiting model is a Gaussian white noise model. And usually if you are in other areas of statistics, if you have understood estimation, all these things, non-perfect estimation, the Gaussian white noise model, you have understood everything. So it's usually sufficient to understand this model. And it's the same, I think it's the same here. So our model is now exactly the same. The only difference is that you observe the full process. So you observe the full process. That's very strange, but if you go to the limit, you observe the full process. And just imagine just get a curve or something like that. So there's no design problem anymore here, right? I mean, because you observe you take observations everywhere. There's no design problem anymore. Okay, so that's good. There's no design problem. That's good. Okay. Okay, so there's, in this sense, we somehow have deleted the design problem. There's only the remaining estimation problem. Okay, and then what I want to emphasize is whenever you do here, for example, weighted least squares estimation in this model, and you calculate the covariance matrix of the weighted least squares estimator, this is always better because here you have more observations. You have infinitely many observations. Okay, so if you do weighted least squares estimation in this model, you are doing better than in this model. Okay, because you have more observations. It's trivial. Yeah, so because you observe the full process. Okay, you have to estimate appropriately. So what I want to do first is I want to give you the best value that you can get in this model. Okay, so what is the best variance that you can get in this model? Okay, that's my first theorem. So I give you the estimator. My first theorem 1. Okay, so the important thing is that you observe it everywhere. Okay, and of course, if you have n equal 100, and then you are close to that one. But later on, I show you that you're already close to this one if you have n equal 5. Okay. So the theorem gives the blue in this model, or the maximum likelihood estimation. So the blue, which is equal to the MLE in model 2, is given by, and I want to prove that, I get a, because it's so simple, it's given by theta hat. Let's call it theta hat. I don't put an index blue. If I would have transparencies, I would always put an index blue there, but I don't do that. So the blue is C inverse. I explained C inverse, some kind of matrix times a stochastic integral 0 to 1 f dot the derivative of s. So this is a vector times s dys. So you might not know what this means. That's a stochastic integral. So you can, it's like a Riemann-Stieltjes integral. It's a little more difficult to define, but it's quite easy. So I have to explain what 4 is. 4 is, not 4, but C is. C is a matrix f derivative of f transpose derivative of s ds. Okay, and if I write C inverse, I assume that this really exists. Okay, so I was quite proud when I found that. Well, it's actually trivia, so some Russians already did this in the 80s, basically. That's really true, but yeah, so it's so you can look at books of Kazminski or Ibrahimov or something like that. So you just have to know that these things exist, that they do some kind of statistical inference for stochastic processes. Actually, the result is not in the book, but you can use the results of the book. So how do you prove that? You need some kind of Gershanov transformation from, yeah, if you do mathematical finance or stochastic analysis. Gershanov, that's okay. How do you tell it? Gershanov?
Yes.
Okay, yeah, okay. But anyway, so G transformation. So what you have to do maximum likelihood estimation on a very abstract space. So say P1 is a measure of yt. Okay, this is a process on the spaces, the space of continuous functions. And P2 is the measure of the error process on the same spot. Then you can write down the likelihood ratio of this thing. So you can write down what the logarithm of dp1 divided by dp2 is. Okay? So this is just the stochastic integral which I've mentioned there. And then you get some square. Okay, so you write that down. So even if you don't know anything about this Gershanov transformation or these things, if you have seen this and you do maximum likelihood estimation, you just have to maximize that. And you can just take derivatives with respect to theta, and you get this. Okay, so you just maximize that.
What about when f is a constant?
No, f is a constant is excluded, you know, then you have to work harder. Yeah, so f is, I mean, as a location model has been clarified for a long time. Okay, anyway, so this is, if f is a constant, we have to do work harder. Yeah. Okay, then we get even more interesting things, but they are unfinished, right? So they are unfinished. We discussed them this week. Okay, anyway, so you maximize this. And you get 3. Okay, so that's the blue. And now you can calculate the variance of the blue. So maybe you do this. So at first you will check if it's unbiased. That's quite easy. If you just do it like a person in physics. Yeah, a person in physics, what would the person in physics do? He would do this one. I mean, this is the, oh yeah, maybe I should. Usually people write the model in this way. You have seen that, right? I mean, this is they write it that way, but a person in physics now would just insert this here. Okay, this would be epsilon t. And then you have f derivative times f derivative transpose. You have the matrix C, which is canceling, and theta is remaining. And then you take the expectation of the remaining integral, and this is 0. So the expectation is theta. And let's left some time. And you can do the same thing with the variance.
Theta not 0.
Thank you. So the variance, you do the same thing with the variance. So we get a C inverse left, C inverse to the right. And if you do a little calculation, then you just have, what did I do here? Yeah, something like that. And you get a C inverse here. Okay, so that's the variance, and now you maybe know or not know Ito's formula, and then you see this is C. So this is C. This is Ito's formula. So this is C. So the variance is C inverse.
So question, you have sometimes a derivative f dot, and in your definition...
Here's also one.
Yeah.
I always forget it.
Yeah, did you forget it also in the model, or...?
No. So there it is correct. Yeah, maybe I mixed it up. So this is the correct. When you go to this differential form, you get the derivative here, and now I have to be careful that I also have it in the likelihood here. Here it is. So everything. So when you go to the... Well, basically what you do is you somehow calculate dyt divided by dt when you move it. Then you get the derivative here. Okay? That's basically, it's a little more complicated, but it's basically, roughly speaking, it's like. Thank you. Okay. So this would be the dream solution. We would be able to observe the full process, and we would be able to do the best estimator. Okay? So that's good. So of course.
That obvious? It's not that obvious.
No.
Because if you can go to continuous to filling the whole input.
No, you have to look at this paper.
No,
it's not quite obvious.
Comment, because
Yeah, it's not obvious. No. We actually derived this blue, then we have to check that the blue is getting the. So in that paper we proved that that C inverse is really the best things you can get. No, it's true.
Since I introduced some density, which is not going to zero anywhere, and started to throw points, infinitely many, accordingly to this density. So I fill the whole space very densely, and my final result, I almost fill everything, you see, continuous observations. Then I change the density, and it will be another result. What you are doing, you fill your space with uniform density.
No.
I'll talk about that.
No. Don't. You misunderstood something.
Talk about that.
No.
You will talk.
I will
Yeah.
talk
No.
about that.
That's not good. You misunderstood something. So we just stay in this model, and if you're in this model, then you can believe me. Whenever you do estimation in that model, the covariance matrix of the weighted least square estimator is larger in the Löwner ordering than this one. Yeah. So that's true. That's easy. Okay. So this is okay. All right. So this is not helpful at all because we start with this model. So now we have to go back to this model. You know the optimal solution, then we have to go back to this model. So we want to construct a good estimator, and I have 2 more blackboards. That's fine. Good estimator and good design. So. We go back now from this abstract theory to the concrete example that we have there. Okay? And yeah, so let's see. So we have these points. So let's say we take T1 equal to zero, and Tn, the last one, equal to 1. So we take the boundary point. Okay? Let's see, that's okay, so we always take them, and then we construct the estimator as follows. We just look at this this representation. If you now I want to, somebody asked why you want to use colored chalk. Yes, I want to do that. If you look at this one, you can write it as the sum. You can split this integral just by integrating with respect to different intervals by the design points. Okay, you just split the range of integration in several intervals and you add them up. So from 0 to 1 quarter, from 1 quarter to 1/2, and so on. Okay, and now it's quite easy. If you want to construct an estimator, you cannot evaluate this, but you can say, well, if the interval is small, this is somehow close to f of ti minus 1. So you just replace the function which varies by the value of the left boundary. So that's some kind, the way the E2 integral is constructed. Okay? So the estimator that I have in mind is, so it's theta n hat, it's C inverse, and now I have to be careful because I changed the notation. I take, and then I get the sum, and then I would do the following. I would do this one. This would just be an approximation of this integral. Okay, and if you know a little bit about quadrature formulas, then you might take a weight here, which I call omega I. Okay, so I just do some kind of quadrature formula to approximate this integral. Okay, and now you see this is not a number. This is when we begin, it's an m by m matrix. So this is an m by 1 vector. So this total thing is a vector again. So this is gamma I is a vector again. Okay, so I write this estimator, say, okay, so that's the estimate. So we don't know the gammas, we don't know the TIs. Okay, but that's the estimator we propose, and now we choose the gammas. Okay, we choose the gammas, and how should we choose the gammas? We have many choices, but we know the optimal solution. It's here. So we choose the gammas. Such that, one thing is that theta hat n hat is unbiased, and such that the expectation of theta n hat minus theta hat, this is the unknown thing which we don't know, but in mathematics we can calculate, is minimal. Okay, so we choose that because then we are close at the best solution in the hypothetical model. Yeah, so we want to go this way. You can actually show that this also minimizes the variance of theta n hat. So So this is also minimizing the variance. So it's also, if you like to have that more. Okay. So I have only one more transparency, green transparency. So I have to save a little space. Okay. So now I give you the solution of that, but I am lazy. I just do it in the case m equals 1. Okay. But then if it's larger than m, you just write ff transposed instead of f squared. So it's not really difficult. Okay, so that's my theorem 2. From now I'm only considering m equals 1, but this is not really a restriction, so it's just for your convenience. So I just give you the optimal gamma I star. So they are now numbers, so so this is just k. I don't write kappa because Maria is saying my kappa is wrong. so I'm hesitating to write kappa anymore. So it's a k. So it's a constant times these expressions. So these are the optimal gamma I star. Okay, and the constant is just some kind of normalization. It's R optimal. On kappa is just a normalization, but it's somehow important. No, it's a kappa. I shouldn't do that. So what is my constant here? Yeah, it's just the integral 0,1 f dot square of s ds times the sum of these guys squared. It's just a normalization, so you can forget about it, but I need it later once again. That's the reason why I write it. Okay. Yeah, I don't know if I should prove that. No, I'm slow and I don't have so much time. So basically, if you want to prove that, it's not really difficult. So you just evaluate this thing with a few applications of Ito's formula. Okay? And then you minimize. At the end, you minimize. Yeah. And not really difficult. But maybe it's more interesting what's the...
Is it just tends to a to 0? You see, your function behaves like a in the vicinity of 0.
No, if it's a to if it extends to a to 0, you get some extra terms. You get extra terms here. So it's more complicated. So I'm cheating a little bit, but otherwise you have to give me 90 minutes. Okay? So because I have to write so much.
I forbid.
no. So it basically extends. Yeah. Okay. Good. So I don't give you this one. Where is it? Now I'm lost. Where is it? This is 2. Okay. No, I will not prove that. So it's basically, if you want to prove that, it's just Ito's formula again. It might be more reasonable to see what you get. So the important point now is if you choose the gamma i's in that way, what do you get? Okay, so what is the value of this thing? Right? So how close are these two estimators? Okay, that's my corollary 3. So it's again m equal 1. For the optimal gamma I star, we get the following. So what is that? So what is this basically measures how close theta n hat is, the variance of theta n hat is to C. So if this is very close to 0, the variance is very close to C. C inverse. Maybe I put a star here. So what you get basically this expression again. So I should have, so this is, you get the integral, so that's our matrix C, but I've write it out. It's not a matrix anymore because m is 1. And then I get these things. And then raised to the power minus 1, and I subtract 1. So that's the result. Okay, so it's again not very difficult. If you finish that, it's easy. Okay, so why is this good? Are these good news? So that's a square, even if I didn't write it very nicely. So if you do a Taylor expansion, I will demonstrate this in an example. So if you do a Taylor expansion here, so this is basically, this whole expression is basically, say, f at an intermediate point, square, because you have the square outside, times the difference of the time points, squared, and that this cancels. Okay, right? So that's analysis, we call this analysis 0 in Germany. Okay, and this is now a Riemann approximation of that integral. So if n is large, This is small anyway. Wherever you choose the TIs, you just choose them equidistantly or something like that. It's small anyway. So the gamma I star and F does not behave too strange. Yeah, I mean, if F is doing like if it's one of Well's examples, then we have to work harder. But right now, for many models, you can go with a uniform design. You don't have to do anything. I give you an example for that. Okay, I give you an example. So,
but it's Riemann approximation only when intervals are the same.
so sorry?
If intervals Ti minus Ti minus 1, if they tends to be uniform, when n tends to infinity. If I changed the length of this interval, limiting length,
We don't do any. So that's
approximation of
well, I know you are very old, but we are going a new way. So we come from the limiting model, and then we construct. We don't do this TI. We just construct an approximation of the best estimator in the hypothetical model. We do it completely. We don't do this limit like as Ilvisacker did or all these people did. We did it in that paper, but we don't do it in this paper anymore.
Sometimes age gives us some privilege to know a little bit more.
No, I mean I respect that. It's no problem, but we don't do this limit. Okay, I give you an example, and you will see. No, maybe I do. You can construct functions where it's not working, of course. And you can do this in every statistics application. Okay, so let's see. No, this is not this is an example where we can do even more. So what I'm saying, my message is, if the function is rather smooth, so if the second derivative is not too large, you can just stay with uniform. Okay? So if you just you have 10 points, and the function is smooth, the second derivative is not too large, takes a uniform distribution, takes these estimators, use this estimator, then you're very close, up to 99% at the best estimate in the continuous time model. Okay? Okay, if it's not smooth, you have to do this minimization. Okay, but you don't have to do it all the time because this is somehow cumbersome. I give you some example here where we did this, or I just did this morning, so this is even new for my co-authors. And so this is so you don't know that. So in this example, you can actually work that out. You try to minimize that. And if you do that and you work hard, you get actually an equidistant design. But I think it's only true in this model. And for this expectation here, you get, I cannot calculate, so you get something with 4n squared minus 8n plus 3. And n should be, this should not be negative, right? I mean, so that should be at least 2, which I think is not a big restriction. Okay, so this is theta hat. So this means if you have 5 observations, this expression is all approximately 0.012, and if you have 9 observations, this expression is already 0.0025. So you're very close to the optimum. So, okay. All right. Okay, so I give you a few conclusions, and then we have some discussions, how smooth F is or whatever. So what I claim is if you know the function, if the function is not so crazy, if it's a Michaelis-Menten or something smooth, it's a low-order derivative, then you just don't do that, just take an equidistant design, then you are quite good. If F is smooth, in some sense. It's difficult to quantify. we don't have. It's not needed. Yeah, you can of course do it, but you usually get efficiencies of 99%, something like that, even if n is 5 or 6. If not, otherwise you have to minimize that. So you get also an expression in the general model, and then you can try to minimize that, or the trace of that, or the determinant, something which you like. But right now you don't have to do that. Okay, so if not, minimize with respect to d2 up to tn. But it's not necessary if n is 100, because if n is 100, the Riemann approximation is already quite good. Then you take the uniform design, and it's also again good. But if n is small, the function is doing, I don't know, sinus 1 over x times x or something like that, then you might run into trouble. But otherwise not. Okay, and this last conclusion is that if we do it that way, then the derived estimator, the estimator I've constructed, is extremely close to the blue. Yeah. But it's not always equal to the blue. Or it's very close to the blue. Okay, and I think I have to stop here, unfortunately. Thank you very much.
Thank you, Holger. Do we have any questions or comments? Okay.
Just a quick comment, Holger. In your theorem 1, you mentioned results by the Russians, and probably you can find it in Ibragimov and Khasminsky in 1979.
That's a book we cited. It's not there because we had to do a little trick. It's on 0, 1, it's there, but if you're on different intervals, you have to be a little careful. That's actually the result we used. Yeah, you have to do a little trick. You have to define the right function to apply the result of Khasminsky-Ibragimov. Okay.
Is it only for Brownian motion result?
This result, Anatol will tell you right now, it's true for any kernel which has appeared so far, for any covariance kernel.
Then somehow, Anatoly, then I lost a little bit. So, first of all, how it related to results of Illusecker and Sachs, who did the similar problem when I still was young.
Yeah, exactly. That's the reason I know it. Yeah, but
so how it's related?
It's not related. That's not
And
related.
that is not very good.
This is better.
No, it's not better. It's my first remark, because if you have different kernels, here kernel, by the way, Brownian motion here, it's not good kernel on interval, first of all. It should be Brownian bridge sooner.
No.
Let me
Yeah,
continue.
yeah.
So Brownian bridge, because here I still do not know. Let's assume that instead of, when you work on integral, then either when you work on interval, integral is not the best thing. Actually, you have to use Stratanovich integral, and then the result could be quite different. And I do not see it here. And there are some interim results when Stratanovich integral going to eta integral, and in this case you can gain something, because physically when you work on how Stratanovich integral came, that there is no direction on this interval, because eta integral assumes that it's in time. You have to put a direction.
Yeah.
Stratanovich integral actually came from radiophysics. It does not really point out a direction. It's spatial integral.
But I'm sure you can do the same. Two remarks to your comments. So that's true. I mean, the basic idea is why we used e to the integral is because we did this construction of the approximator of the estimator. But we can also use the Stratanovich approach to put something different here.
Yeah, but limits could be, and that's why I say this limit of uniform distribution is not what actually Sachs and Illusaker think about or thought about, because they actually look for optimal distribution, limiting distribution of points, how you converge to continuous case.
And we don't do that. I mean, this is the point.
I understand that you don't know.
Yeah, so we don't
but
do
that
that.
should be done.
No, I mean,
Did you
We-
refer to their
of course, and we compared it here. Even here, we are already better.
Can you try to move the discussion off my
Yeah,
automatically?
right.
Because I will
Yeah.
give you more information about it.
Yeah, so that's right. So what I want to once again, this Brownian motion kernel is just for this talk. I mean, this is what Anatoly is telling you right now. It's basically true for every kernel which has appeared so far. We just do some transformations of the models.
I will be very pleased with
Yeah, so this is
Just a comment that, as a robustnik, I'm pleased that the optimal design here is the uniform, because it's also very robust against having made the wrong choice of an autocorrelation function.
yeah, but it's this is
It's a winner on 2 counts.
yeah, but this is just here. It's just for the special examples that's a uniform. Otherwise, it's not the uniform.
Linda?
Going back to a totally naive question, but if I look at theorem 1, if you'd asked me to write that result down, knowing what I know about linear models,
This one?
yes, that's what I would have written. I mean, it's like x transpose x minus 1 x transpose.
No, of course, it's like that.
So,
It's just it's like it's just a
yes.
the
In a way, my question was, can you not go in the other direction from the discrete to the continuous?
that's what they did before.
Sorry?
That's what they did before, like Ilvisecker or something.
Okay.
But I think that they didn't come very far because they don't have any explicit solution. For example, I did this in 10 minutes here. Yeah, so it's because we're going a different way. But if you start with this discrete and doing all this, that's what we did here. We started with discrete stuff and did the limit. But at the moment, at least I'm not sure about Anatoly or something or Andre. At the moment, I'm thinking it's better going from the opposite, starting from the limit.
I think we need to move on. Thank you, Holger.